to jump on this call. I'll try to keep it as exciting and as interesting as possible, considering that we're discussing electrical heat tracing. So I'll do my best. Doesn't look like it's really too large of a group, so I have no issues with, if you have any questions, typing them into the computer, speaking up, however you want to get my attention. That way, if you have any questions, we'll handle them directly, or feel free to wait till the end as well. It's going to be somewhat brief and not too in-depth on any particular subject within electrical heat tracing. It's going to be more of an overview on the fundamentals of heat tracing, as well as our design tools, or our design tool being TraceCalc Pro we'll discuss today. And then a little bit into some photographs of correct and incorrect heat tracing installation examples. And then we'll open it up for discussion. And we'll talk a little bit about insulation as well, since insulation is an integral and absolutely necessary portion of any electrical heat tracing system. So I'll get started here. Give me just a moment while I attempt to share my screen here. I have 3 monitors and sometimes it's a little bit buggy. So give me just a moment, and then if someone could let me know if everything's coming through nice and clear. Okay.
Looks good.
Looks good? Okay, great. So again, this presentation today will be about electrical heat tracing specific to the industrial market. nVent is the manufacturer of Raychem and Pyrotechnics electrical heat tracing systems, as well as the controlling monitoring systems, cable components. Today we'll be mostly discussing the industrial segment of our product line and services. So that's what we'll get into today. So we're going to start off with hopefully being able to, there we go, the basics. So really the purpose of heat tracing is to maintain flow or maintain a specific temperature. And that an important word there is maintain, in that we are trying to maintain the temperatures and not heat up applications. We can get into heat up applications where you're trying to increase the temperature of your flowing process. You can do that with heat tracing, but it is very few and far between. So what we'll get into now is just a little bit of discussion about, the first thing will be when we design heat tracing systems, what is our thought process? What is our real goal here? And our goal is to maintain an existing temperature, or maintain a temperature, if you have a temperature higher than, for example, 40 degrees Fahrenheit, and it's for freeze protection, we want to maintain that temperature or keep that temperature from dipping below 40 for freeze protection applications. So maintaining flow, preventing freezing. Freezing obviously causes expansion, broken pipes, valves, things. So that's really the majority of applications with heat tracing, as opposed to a heat up application. Keep in mind, we also get into process maintenance, and that maintained temperature can be a very high or elevated temperature. So we're going to get into a little example just to confirm and hammer home the idea and how heat tracing is designed and how it typically is used. So if you look at, for example, this is a 3-inch diameter metallic pipe. It is outdoors, and we will design on worst case scenarios. So we'll say it's outdoors, it's minus 25 degrees Fahrenheit, and the wind is blowing at 30 miles an hour. So this little analogy we're putting together may seem a little bit extreme, but actually it's not too far off. To give you an idea, locally in the Northeast United States, at least around the Philadelphia, New York, and surrounding area, our typical minimum ambient temperature we're designing to is minus 10 Fahrenheit. And you really don't need to go too far north to run into minus 25 F applications. So for this little analogy, we'll use minus 25, wind speed of 30 miles an hour. So when we look at your heat tracing system and we're designing a system, and we're more importantly sizing the cable, choosing the correct cable for your application, what we're doing is we're looking at a single foot length of pipe section. And within that section is just a spool piece. We're not factoring in any valves, supports, and flanges in that particular portion. Looking at a straight length of pipe. So in this analogy, you can see that a pipe with no heat tracing or insulation, the heat loss is very high. So we have a 3-inch diameter water line. It's outside. It's minus 25. Let's say the water is in there. It pushes through and it stops flowing, and it's at 40 degrees. Well, you can see at 40-degree process, and it's minus 25 out, winds blowing at 30 miles an hour, your heat loss through the wall of that pipe without any insulation or heat tracing will be 100 watts per foot, which is very high. In the next slide, you'll see it really hammers home the importance of insulation. And the reason I'm mentioning that is it's not uncommon to get a call or an inquiry and people are discussing heat tracing and they want to heat trace the pipe, but they sometimes have no plans on insulating the pipe. We quickly had to correct that in that there's not really any heat trace that I'm aware of out there in the industry that can really heat up an application or even guarantee any maintained temperatures without insulation. What happens is no matter how much energy you put or try to put into that pipe or how much energy you're putting through that cable and what the output is, a large majority, over 90% of that energy is dissipating into the air and not getting into the pipe. So insulation is an absolute must, and you'll see that in the next slide, just in the heat loss difference. So right now we're looking at bare pipe with 40-degree water in it. If it gets real cold, minus 25, 30-mile-an-hour winds, you're looking at 100 watts per foot. So now we're looking at the analogy. The only thing we changed is we added insulation. We don't have any heat tracing here. We just added insulation. So right, this analogy is 1.5 or 2 inch thick. Let's say it's a mineral wool, which is a common insulation. You're really going to increase the time that it's going to freeze. And I'll go back. You'll see this one with this application with no insulation, it will freeze in less than an hour. And what's the insulation doing? It's not preventing freezing. It's buying you time, which is why heat tracing is necessary. So we have the same application. We added insulation, and now we're bought ourselves 10 to 20 hours as opposed to an hour. And now here you can see our heat loss has greatly decreased. It really, the insulation, what it does is it brings down that heat loss into a more manageable level. Now we can do something with 5 to 8 watts a foot, as opposed to a cable that we're trying to compensate for no insulation and put it at 100 watts per foot cable. The KW on a heat tracing system of that kind of output would be extremely high, and there still would be no guarantee of its effectiveness. So now we have a pipe. It's minus 25, 30-mile-an-hour wind speeds outside. We have the heat loss down to a manageable level at 5 to 8 watts a foot due to the application of insulation. So now we get into maintained temperatures here and what we can do with the heat tracing. So like I mentioned earlier, the top description right there is a pipe with no heat tracing, just insulation. You can get away with that. Sometimes that can help if it's not a really critical application, but it really is only a matter of time until that pipe freezes. The insulation is not preventing freezing, it's just buying you time until freezing. So you can give you the idea that you're saving your system if things are taken care of, if you get through a season or two with insulation only and not heat tracing. But really, it's a gamble, and it's only a matter of time until we get enough low temperatures for enough long period of time that it will freeze up. And that's where the heat tracing comes in. You can see here on the top one, with the insulation, the temperature does dip down and slowly go down and will get to a freezing level and well below in time. At our heat tracing, you can see that the temperature going across through time, it's not increasing, it's not decreasing, it's just staying the same. That's mainly the goal of heat tracing, is not to heat something up, is to prevent it from cooling down and keeping that temperature, whatever that desired temperature is, 40 degrees for freeze protection or any elevated temperature above that, is just maintaining that temperature in a straight line. And that's what we're trying to do with heat tracing. Not a lot of dips and valleys in that, definitely not a dip below freezing or a spike in causing degradation of your process. So now what we've done here is we did our heat loss calculations on this application. We have a 3-inch diameter pipe, we put our insulation on, and if you remember from the first 2 slides ago, we said our heat loss was around 5 to 8 watts per foot. So since that's the energy being lost from that pipe through the insulation into the air, Now we're going to just simply replace that same amount. Again, not heating up. That's what's being lost through the insulation. So let's replace exactly what's being lost with our heat tracing. And that's how we maintain those temperatures. So methods of heat tracing. So there are a handful of technology. Actually, there's more than there's a bunch of technologies out there to heat trace piping. It can be from circulating fluids with jacketed piping, even with external tubing, similar to steam tracing. There's electric tracing. There's impedance, inductance heating, skin effect systems. All different types of applications. Today, really, what we're going to get into are primarily or strictly actually electrical heat tracing, and with two technologies of electrical heat tracing. Reason being is that is a large majority of all electrical heat tracing, or even heat tracing in general, is done electrically now, as opposed to a lot of steam in the past. There's a lot of benefits. There's some cons to it as well, depending on how you view energy and costs. But really, the market has been and is still going towards all electrical heat tracing for most applications. Of course, there's these other technologies out there that we are directly involved in with the MI cables and self-regs. They all have their place, but today we're discussing which is the large majority of applications, which is handled by a self-regulating cable or an MI cable, and those are the two we'll be discussing mostly today. But this slide I like to keep in here because it shows you that there are a lot of technologies out there to achieve things, but the electrical heat tracing way is the most cost-effective and most easily controlled in most of these applications. And to take another step back here is when I say electrical heat tracing systems or HMS systems, heat management systems, when we as a company don't look at strictly what we put on the pipe, or it's not just strictly a cable and components conversation, it's an entire system. As you can see here, when I get involved in these heat tracing applications, sometimes the customer or the engineer is often surprised that I'm asking questions that may seem that's out of my scope. I'll be talking about the insulation, I'll be talking about the power distribution, the control and monitoring, the transformer, everything back in, because all of this plays into the design of a proper heat management system. So when I discuss management systems, this is typically the scope that I am considering and thinking about, and typically like to get involved in and have some influence over, or at least knowledge of when I get into this, so that I can properly design a system. Because if I'm strictly looking at on pipe only and I don't have a full understanding of what's going on upstream or downstream, it limits me on my understanding, and it limits me from choosing the best possible product for that application. So I like to know what's all the way back to the transformer feeding the panel, the types of distribution, types of conduit wire it's going to be pulled, including all the cable that goes on the pipe, as well as the insulation, jacketing, and what type of environment all this equipment is in. So right now we'll talk a little bit about the self-regulating technology, which is again the largest portion of heat tracing in the world is done with self-regulating technologies of electrical type. So what is self-regulating and what is not self-regulating? I'll get into that and a little bit about how it works in these next few slides. Common misconception I'd like to get out of the way is that people will sit and rightfully so will hear the word self-regulating and assume that you slap the cable on the pipe and somehow it knows what temperature, or that cable is for a specific temperature. When we have lots of different flavors and sizes and types and outputs of all of our cables, but no, there isn't a cable that is really assigned to a specific temperature. They are different outputs and different characteristics for different reasons, which we'll get into. But with self-regulating cable, it does self-regulate. However, it does not shut off. It will always have an output, whether it's a watt or even less than a watt or a few watts per foot, no matter what the temperature is. So it does not shut off. The reason I mention this, and I'm pretty firm about it, is that there's some applications that I see and still run into quite often where over temperature or overheating is an issue. and a lot of that comes from a misunderstanding of self-regulating cable and the name of self-regulating. So, for example, the application I like to discuss is, where I see it most often, is with safety showers in the industrial environments. So safety showers are obviously very important. They need to be maintained, they need to be operating at all times and fully functional. And a lot of times what I will see is that people say, okay, I have a safety shower system. I want very high reliability. I just don't want it to freeze. We've got to keep these things flowing at all times. So they'll try to pull the control and monitoring system, whether it's a thermostat or electronic controller, out of the scenario to increase reliability. And that makes sense in that if you have less parts, there's less points of failure, you have a more reliable system. However, when you get into uncontrolled, I'll say, systems, and you're trying to rely on self-regulating cable to maintain the temperature, we can get into over temperature issues. And what I have seen numerous times through the years is that exactly that on the safety shower line. They have even our lowest output cable, which is our 3 BTV cable, a 3 watts per foot output. They will put that on the pipe, they will put it on a breaker, no thermostat, and just let it cook. And that way they know that, okay, we have a breaker and I have a cable, minimal points of failure, it should be reliable and it should be always be on. And it is. The problem with that is that since if it's left on indefinitely, it will slowly trickle heat into that pipe. And with safety showers, there's not a lot or hardly any flow. So that water is sitting there and it's stagnant and it's slowly absorbing that energy. It is not uncommon if you let electrical heat tracing, a self-regulating cable, cook in that line. For example, I've seen like a 1-inch diameter copper pipe and that water get up to well above 120 degrees. So you can imagine going to a safety shower, an eye wash, or whatever it is, and expecting relief from whatever happened that you need the safety shower for, pulling that chain, pushing that lever, and you get 120 degree plus water in your eyes, face. Obviously, that can be even worse than what you went to the safety shower for relief. So I always recommend, not just in safety shower applications, but in any application, some type of control, even though it is a self-regulating cable. It self-regulates, it will vary its output based on temperature that it's in, but it will never shut off, is the summary of all that. So I like to discuss that strongly. So how does it self-regulate? We'll get into that here. So you can, I have a video that I like to play, but it doesn't work well with doing this remotely, so I haven't been successful with that. So what I'll do is I will send out a link directly to that video that shows better than I can verbally explain how the self-regulating technology works. But in summary, with this little diagram here that you see, is the magic or the technology behind self-regulating cable is in the carbon polymer core. If you cracked open or sliced open one of our cables, you pull away a couple outer jackets, you pull away a metal sheath, you pull away some layers. Those layers that you're pulling away are strictly for electrical and mechanical protection. Not really the function or the meat or the action of the self-regulating cable. What the self-regulating cable meat is, you have in this diagram, you'll see your 2 current carrying conductors going down the length of that cable. And the first thing I like to explain is those current carrying conductors are not heating elements. They are strictly delivering electricity, power, energy to the heating element, which is all along the length of the cable. So they are not heaters. What you get is the carbon polymer core that is extruded around those 2 conductors is your actual heating element. So you can see let me see, I don't know if you can see my mouse here through here, but you can see this portion here in between those conductors. That is the actual heating element all along the length of that cable. And what happens is that carbon polymer core, when it gets cold, it contracts. When it contracts, it microscopically contracts and creates additional heating paths in between the 2 current carrying conductors. Now, conversely, when it heats up, it expands and creates less conductive paths. So that's how the cable physically regulates itself all the way along the length. So that's a better understanding is you could have an application where we have a cable that along the exact same cable, same circuit, same breaker, everything's the same. A few feet of that cable is putting out, let's say, 3 to 4 watts per foot. But you could go down the run where that cable is in a colder environment for various reasons, and it's pulling double of that, all along the same length of the cable. So that's how it self-regulates along the line. It reacts by expansion and contraction of the carbon polymer core along the length of that cable based on the ambient temperature that that cable at that point is experiencing, if that makes sense. So that's how it self-regulates itself. And I'll get into another point with that is that electrically, when you're doing your load calculations, it's important not to use Ohm's law in looking at it. So basically, and that happens often, and it's a constant battle to keep everyone in check and not overloading the breakers. And it does get confusing. For example, we have 3, 5, 8, 10, 15, 20 watts, various wattage per foot cables, and that's how we list them, sell them, and describe them. But however, that real output is different than what it's labeled. So what we've done as an industry, not just Raychem, but everyone in the industry, they decided, okay, let's label all of our cables at what the output is of that cable when the cable is in a 50-degree Fahrenheit ambient environment. So keep in mind that if you buy a cable and it's 10 watts per foot, you can't just say, okay, I'm going to do Ohm's law. I've got X amount of foot of cable, 10 watts per foot. I can load up the breaker. The problem is if you have an application that cable is going to be in an environment that's less than 50-degree ambient, it's going to pull more than 10 watts per foot. So your calculations are already off. And once more, to make it even worse, during a startup, when that system first starts up, there's an inrush because that cable is typically much colder at startup, sort of like a motor. There's an inrush to it. Same thing with self-regulating cable. So what we do is people say, well, how do I figure out the maximum circuit length? Is we have guides and some documents to help you figure out how much cable you can run of a certain type based on a certain voltage and amperage. So your maximum circuit lengths are already determined for you by us to prevent your overcurrent situations on your breakers. Now I'd like to just show a little bit of the reality. So you have a little bit of understanding of what the cables are for, how they actually work. It's pretty easy to understand that when we're heat tracing a straight length of pipe, you're just running a straight length of cable down that. Now, when you get into some nuances of the actual installation is where you don't have a straight spool pipe. You have that pipe where there is a flange, there's a support or a valve, and in this case situation, a pump. So you don't really have to oversize the cable for that. We size our cable for the straight run of pipe, and let's say in this analogy, it's 10 watts per foot, and then we come up to a pump. We will do heat loss calculations on that pump to figure out how much wattage that pump needs to prevent from freezing. And then we say, okay, well, we're already using a 10 watt per foot cable on that pipe. How much of that flavor cable, that type of cable, do we need to apply to this pump to prevent it from freezing? And then we come up and we calculate a footage in our design. And that leads me to show another thing is that often a misconception is that someone will call and ask, and we'll be discussing an application, and I'll ask what footage of pipe is in this project, and they'll say, let's say it's 1,000 feet of pipe. And then we work up a design, and we end up quoting them or coming up with a design that includes 1,600 feet of pipe. And they're kind of taken back. If I only have 1,000 feet of pipe, why is there so much cable involved? You have to do an additional wrap for all your valves, flanges, supports, along with an extra loop for all your components for a service loop. Service loop being if that component breaks or gets damaged or needs to be pulled away from the pipe, you have some slack in that cable. So that's not really uncommon to have a ratio of 1,000 feet of pipe and needing 1,600 feet of heat trace cable. That's really kind of a typical ratio of cable to pipe. And you can see here, and this kind of hammers at home, is how much cable is being wrapped, how much footage of cable is being wrapped around the pump, and also including the flanges and the other things that are included in all those equipment right here. It really does eat up the cable pretty quickly. Another application I'd like to show in that often people will think heat tracing is strictly for piping systems. We can heat all different types of equipment. I'm not sure what exactly this spherical tank was for, but it gives you an idea that no matter what it is, if we're able to insulate it and get the cable on there, we can heat it up. Through the years, we've done catch pans to grading, window mullions. We also have direct applications. We have product lines specifically for roof and gutter de-icing, snow melting, floor warming. So we can really do a lot with heating cables of this type. So keep in mind that even if you're unsure if it's not piping or a tank, if you're unsure, just give us a call, and 9 times out of 10, if you have the power available and we can get some insulation on the piece of equipment, we can heat trace it and get it to the temperature that you need. So I'll get into a little bit some of the pros and cons of a self-regulating cable or polymeric cables versus some other technologies. And a most important one, and one of the many reasons that a self-regulating cable, as I mentioned, is the predominant technology out there in the industry, is ease of installation and lack of front-end designing needed to really get product out the door and the project completed. With self-regulating cables, you can cross them all over the top of each other. You can tauten up and do a knot. You can actually power it up when it's on the reel, all bundled up together, and it won't hurt itself. The self-regulating inherently, if it's next to each other and it's crossed over each other, like you see in the picture on the right, it will sense the heat from the other cable, and that heat will cause it to expand and therefore put out less power, less heat. As opposed to a non-self-regulating cable, which you see on the left, crossed over is a problem. You get hot spots and burnouts in that area. Is it a big deal? It's not huge, but it's something that when you have a project and there's thousands of feet of this cable being installed, and then it's going to be covered up with insulation after the fact, you want ease of installation to make these things go smooth. You don't want to be worrying about a cable crossing over somewhere, causing a hot spot and premature failure. So that's one of the great nuances to the self-regulating cables, that you can wrap it on top of each other. You don't have to worry about it laying next to each other, crossing over, whatever happens. Now, we do have some other technologies that we sell that crossing over is an issue, but self-regulating is not that problem. Other thing about self-regulating, I'll say, is that it can be cut the length in the field. If you're unsure of exactly how much length of cable, we can get close. We send it out on a reel. You can pull it off the reel as you install it, and then when you're done, you're done. Just watch your footage. As opposed to, which we'll get into a little bit in just a moment, the MI cable technology, which is a great technology. It's an older technology. It's still needed, not as common anymore, but it's much more design intensive and installation intensive, and we'll get into that as well. So MI cables, which I just mentioned, MI standing for mineral insulated. There's a magnesium oxide insulation inside this tubing, I'll call it. It actually starts as a pipe, but as your insulating factor between the two current carrying conductors. So MI cable. In this little picture, we'll say, I know it's a large picture right there, but most of our MI heating cables, which is, and I'll say this again, this is a separate technology outside of the self-regulating technologies. This is a series resistance technology, or a toaster wire. Just a resistor is what this is. So it's a large diagram here, but you'll see the seamless metal sheath. In reality, the typical OD of that, when it's sent out, is, let's say, 3/8 in diameter, or a 1/4 inch diameter heating element. So it's a big blown up picture, but that's typically a very small heating element. And then inside you have your magnesium oxide powder, which is your insulator, and that is to insulate the two current carrying conductors, the solid conductors, from touching each other. So that's your insulation. So you have the metal sheath, which is your outer jacket for protection, your magnesium oxide, which is your insulator, and then you have your current carrying conductors and your heating elements inside, protected from touching each other by the magnesium oxide. So when you look at this, this is a good diagram because it shows exactly what's in there. You would get this tubing sent out to you, and it's pre-terminated. The power connection end and the end cap where it is terminated is already pre-terminated and done for you. There is no termination of those actual solid conductors done in the field. For example, when this starts out, like I mentioned, let's say the OD of that seamless metal sheath, let's say it's 3/8 or a 1/4 inch. That may start out as a Schedule 80 1/2 inch diameter pipe. And those solid conductors, when the product's sent to you, may be something like 18 or 20 gauge conductors, so very small in diameter. But they start out, what you could say, 12 gauge or 14 gauge. So what we do at the factory is we have this, for example, a 1/2 inch diameter Schedule 80 pipe, and then we pack it with let's say our 12 gauge conductors and magnesium oxide. What we do is we extrude it and we extrude it and we pull it and we stretch it until it becomes a diameter that we want. And what we're trying to do is stretch it out to get those current carrying conductors to the diameter that we want to create a heating element, is basically what we're doing. Now, the reason I mentioned this manufacturing process is that, as far as I know, we are the only company in the world that manufactures it this way. We start out with a pipe, we put our conductors in it, magnesium oxide, and we basically stretch it out through dies. Every other manufacturer that I'm aware of, what they do is they will start out with a flat piece of metal, some flat bar stock, and they will pull that through a machine and fold it on top of each other, and just kind of curl it around each other. And then robotically, they will weld it all along there. So what you have is you have a seam all along the heating element. No matter how good that weld is, having that seam there is a point of failure. And even if it's microscopic, it can cause failures. And so the reason we put all this effort into doing it this way by pulling it is to keep moisture out of there by reducing that seam to keep moisture out of there. Why are we so adamant about that? Is moisture is the enemy of magnesium oxide insulation. It wants to wick moisture in, and once it's in there, it's going to cause shorts, ground faults, all kinds of issues. You're going to have cable failures. So keeping that inside of this MI cable dry is absolutely paramount, which is why truly the manufacturing process that we use is by far superior than anyone else, because simply there's no seam, there's no point of failure all along the length of that cable. So you may ask, well, if we have self-regulating, it's so great, why are we still manufacturing and applying an MI cable product? So a lot of the times, most of the times, it's temperature. So when you have these polymeric or self-regulating cables, our maintained temperatures and the temperatures the cable can be exposed to is limited. Really limited in that most applications that are out there that we run into, the self-regulating and polymeric are fine. We have technologies that we can maintain up to 250 degrees Fahrenheit and higher with our self-regulating cables. However, the products that we use, the materials that we use, the polyolefins and the fluoropolymers, they have their temperature constraints. So when you get into applications above and beyond those temperatures that the polymeric cables can withstand, that's when you jump to an MI cable. They can maintain much higher temperatures and they can withstand much higher temperatures. They can also take a whole lot more physical abuse. So for example, if there's an application where there's high potential of this cable getting hit, knocked around, jammed through the insulation, it's stepped on, maybe MI cable is the application because it's just much more robust. You have basically a metal tube jacketing that's very strong as opposed to a plastic jacketing. So you get higher temperature maintains and exposure abilities, as well as a much more rugged product is what you get with MI cable. And I don't know if my percentages are exactly right. With electrical heat tracing now, 90% of electrical heat tracing right now, maybe even more, is done by either a self-reg or an MI cable technology when you talk about electrical tracing. And here I like to show another application of MI cable that's not for heating, and also on the left, how you typically would apply this MI cable. And it shows you the complexity of installing that. So on the left, you'll see it says Raychem XMI heating cable. That's our MI heating cable that we're using. I imagine in this application, there is either a high maintained temperature desired, or that piping is going to be exposing, or that process that piping is involved in has a high operating temperature, an operating temperature above and beyond what a self-regulating can take. So that's when you come into MI cables. So now, why would we want to default or always go to a self-regulating cable if we can, and stay away from an MI unless the temperatures actually force us to? Is you can see on the left the complexity of installing that. So when you're installing a polymeric cable, you can kind of imagine it's kind of like a stiff extension cord. Comes on a reel, you pay it off the reel, you cut it, you wrap it around, you move it, you tape it, and it's on there. When it comes to MI cable, it's more of a stiff tubing. You typically will use tubing benders to install it. You also have issues with MI cable in that it work hardens. So for example, some types of metals, when you bend them and you continue to bend them along the same point, only takes a few bends and it'll snap. MI cable is similar to that. So working with MI cable is more difficult. It's also pre-terminated, which means it forces us as the manufacturer to design the system perfectly ahead of time. I'm going to need to know exactly what you have going on with your piping, no guesstimates on footage, no guesstimates on valves. We need to know everything so that when we send out our cable, it's the right length and the right output for that particular section of piping. So you can see it gets a little bit more involved when you get into MI cable, as well as the installation issues. So that's that. Now, I'll quickly discuss another area of MI cable. Has nothing to do with heating. I mentioned that we start with, when we're manufacturing the MI cable, we draw out and we pull through dies and stretch that cable out to reduce the size of those carrying conductors and turning in the heating elements. Well, what we do on another application with MI cable is not stretch it out so much. We will stretch it out, but we will pay attention to, well, how far we're stretching it out, and we will stretch it out to a specific gauge, whether it's, I think you can go up to 8 gauge, 10 gauge, 12, whatever it is. So this is an MI cable application that is for a current carrying conductor application, not for heating. The example is for let's say a tank terminal, and they're storing a lot of fuels. Well, through that terminal, there are probably pumps and fire suppression systems, and those systems sometimes are powered by electrical pumps. So, for example, if you had a fire in your terminal and you had electric pumps feeding the fire suppression system, you would want to make sure that the conductors and the power feeding those electric pumps aren't going to fail due to fire. That way, they're not failing when they're needed the most. So what you can do is you can use our MI cable basically as a current carrying conductor, as a power feed to those pumps. And our MI cables are rated, depending on the type and exactly the configuration of the cable, rated for 2 hours at 2,000 degrees, things like that. So you can see that we can guarantee that if this current carrying conductor or this conduit or our power feeding that pump is, wherever that conduit run is, if that's under the fire, over the top of the fire, within that fire, it's still going to deliver power to that pump. So that's just another application of MI cable we get into, and we can just consider that fire-rated wiring. The other way it's done without MI cable is using your standard conduit and wire, and you're insulating that conduit, sort of like it's a heat trace pipe, but you're insulating that conduit with fire suppression insulation. Is really what you're doing. You have your regular THHN or THHW conductors in there, and you're kind of buying time and keeping that heat away from those conductors by insulating the conduit. That's one way to do it. But then there's the MI cable wiring. Now the pros and cons of that, imagine the cost involved. So if, for example, if there's a lot of tray out there, or even if there's not tray, you can run our MI cable fire wiring without conduit. It is the conduit, and that's all code and it's rated. So if you needed to run power and to a fire suppression pump, you could buy our MI cable, run it, terminate it, and you're done. Or you can run your conduit, pull your wire, and then insulate all that conduit and jacket all that. And the price comparison, it's a no-brainer when you start looking at the numbers as the price of our MI cable fire wiring versus conduit and wire installation and then insulation and jacketing. It saves a lot of money. So that's the other important application with an MI cable, a non-heating MI cable. So briefly here, I know I'm going a little bit longer. We have a design tool. It's called TraceCalc Pro. So all these nuances and design criteria that I've been discussing, temperatures and minimum ambience and maintain temperatures and exposure temperatures, all that stuff really is integrated into our design tool. I use the design tool very often for all my heat trace designs. Also, when I'm on a call with someone and I'm trying to pull the correct data from that person so that I can properly design their system, what I do is I open up TraceCalc. The reason I do that, and I'll show you here, is that the first pane of the design software, this little screenshot here, it shows you and it asks you all the questions that I typically will ask a customer, designer, engineer, whoever's involved in this. This is the data I want to pull from them. For example, what type of pipe? Is it carbon steel? Is it copper? Is it PVC? Is it CPVC? What is it? The type of pipe. What's the diameter? How long is the pipe? What voltage is it? What maintain temperature are we trying to maintain? You can see the minimum ambient, the maximum exposure temperature, which is important. All these are the tidbits of information I need so that I can come up with a solid and confident design for you. So TraceCalc is a great design tool. Other thing I really like about it is that a lot of our competition has some design tools out. I don't think they're nearly as good as us of sharing the raw data. This design tool isn't just going to grab the information from you and then spit out a list of stuff for you to buy. Can we do that? Absolutely. It can give you a bill of material and exactly everything you need, give you part numbers, the whole bit. But it's also really good at displaying the heat loss calculation data, why we came up with 5 to 8 watts per foot. What is our electrical load? What is the line list involved in this? Is it accurate to reality? It's really a great tool for sharing that information and really just discussing back and forth so that, hey, here's the design I did for you, and here's all the information I put in that design. Do you agree with that? Does that look accurate to you? That way it just really irons things out and smooths things out in the design process. And I already discussed this a little bit as far as the outputs from TraceCalc. A lot of good information, and it's quick, and any design that we do automatically has that integrated into it, and we can easily pull that information out. The other thing that we'll keep in mind with our design tool is, and I briefly went over that, is we can do this for piping, and we can also use this tool for tanks and vessels as well. So we have a specific section of the software now that specifically gets into designing heat tracing systems for tanks, vessels, or equipment, as long as we have the decent dimensions. So we can get into that. Last portion about the TraceCalc is that we have a heat up and cool down calculation tool. That it's not uncommon that someone will be concerned about their process in that power outages are an issue. They'll say, okay, our grid is unstable, we often lose power, so on and so forth. You know, how do we handle that? Well, how long is it going to be until this pipe freezes with that insulation on there? With all of our designs, we can provide a heat up and cool down calculation for you and kind of give you times. So for you have a tank, let's say a tank instead of a pipe, since we've been discussing piping only. You have a large vessel and it's heat traced and insulated, and you're maintaining it at 95 degrees. And when it gets to 70, that product gels up. Okay, and the power outage is imminent. You know you have them. So we can do some really quick calculations and show you some graphs and good outputs on that. If we have an operating system on that tank, it's maintained at 95 degrees, and we'll say worst case scenario, it's a cold day, it's -10, the wind is blowing, and your power goes out. Okay, well, how much time do you have to before that temperature dips down and becomes a problem? We can run those calculations for you. Conversely, we can do the same thing. Is that, for example, if you have a heat trace tank, or you want to heat trace the tank, and we're designing a system, and you want to maintain that tank at 150 degrees Fahrenheit, but when the truck shows up and offloads into your tank, it's showing up at around 120. And you can't use it until it's 150. Well, how long is it going to take for that electrical heating system to take a tank full of product at 120 up to 150? We can run those calculations and show you, okay, when you get offloaded or delivery of your material, you're not going to be able to use your tank and for X amount of hours. So we can do a whole lot with this design tool other than spit out a bill of material of stuff for you to buy. So I get into a little bit install issues and some somewhat embarrassing installations we found through the years. And really, it's not really to pick on anyone or anything. It's to show you the importance of doing it right, and how there is a correct way and a specific way to install heat tracing. And we'll show you some ones that are not correct. And these are really common. So you can see here, we have a heat tracing cable, which is probably sized right for that straight run of pipe. But when you get to a valve, or that flanged valve right there, you need to apply additional cable. You need to do an additional loop wrap of that valve. You can see that there's more mass there at the flange and the valve. And there's also, when that pipe does get insulated, insulation is not going to cover this entire actuator right here. And the actuator is connected, physically connected, metal on metal contact. So that's going to be pulling heat out of this larger portion into the actuator and dissipating it into the air. So you want to compensate for that additional heat sink by adding cable. I can tell you right now that application right there with that cable going over that valve will freeze up in any normal application in one winter. You have to put a wrap of X amount of feet, and I'm saying X, it depends on the temperature that you want to maintain, the size of it, the minimum ambient, all that stuff. But you'd say, and it wouldn't be uncommon to look at a valve that size and say that it needs 6 to 7 feet of cable as opposed to that straight run of maybe 6 or 7 inches. So that's typical mishap, in that people will go right past those additional items within that pipe and then wonder why there's a freeze up. And you can see the same thing on the bottom right picture. Look at it, it's going straight past. It also looks like it's installed using a duct tape, which we definitely don't recommend. Yes, it will work temporarily. We sell tape, and the reason we sell tape specifically for heat tracing applications is that it's not just your regular Home Depot tape. The adhesives that we use in our tape that we sell are designed to withstand high temperature exposure and not basically dry out and become no longer effective. Your standard tapes like electrical tape, your duct tape, those heat adhesives will last maybe a season. If you want to pull off insulation after a few months or a year, that cable will just be probably sagging down and sitting at the bottom of that pipe, which is where you don't want it all the time, typically. Some more issues here. We have some going past valves again, all over. Looks like they have some chain wrapped around that one here. I'm not sure what's going on there. The chain would concern me if I went out and looked at that, in that all electrical heat tracing, whether it's of any technology, by code needs to be ground fault, 30 milliamp ground fault protected. So obviously with the ground fault protection, there's a high level of sensitivity. So you have to be very weary of ground fault issues and causing nuisance tripping. So you don't want anything like metal like that wrapped around like chain, wrapped around that cable, potentially nicking that, causing a ground fault issue. That's a headache waiting to happen. And when you look at these photos, it may seem like it's not a big deal, but if you heat trace, a whole bunch of pipe and then cover it up with insulation, and each circuit is a few hundred feet and it's tripping out, well, where is it? And I can tell you right now, there's no easy way to identify where exactly that issue is under the insulation. It's a hunt and peck game, and it becomes costly. And the other option is pulling off the entire heat trace run, which is expensive. Not only is the heat trace a little bit costly, but a majority of the cost of that type of repair is in your insulation work. If you look at a typical heat tracing system in regards to costing, a large majority of the money is in your insulation material and installation. That's the most labor intensive. I always find it surprising when often when you're getting involved in a project and they're really scrutinizing the cost of the heating cable per foot, and they're not paying attention much to the insulation type or thickness or optimizing that insulation system. When really, when you looked at that, a large majority of your costs, it depends on the project, but you could even say 60 to 70% in some applications of the cost of an HMS system is in the insulation. So that's why we like to get involved early and start hopefully influencing that system so that you're not putting too less insulation on and then trying to compensate with more heat, or you're going overboard on the insulation when really you could just put a few more watts per foot and go a whole lot less. So we like to get involved in kind of, we call it heat tracing system optimization, is kind of find that marriage, that right amount of output, that right amount of insulation that makes sense monetarily and heat loss wise. And here's another misapplication. This is somewhat, it looks like some type of hopper or maybe a catch pan of some sort. I don't know what was going on here, but even if this was going to be heavily insulated, even in a warm climate, I can tell you just by looking at that there's not enough heating cable on there in comparison to that surface area to really have any effectiveness. On top of that, the duct tape on there is a really bad way to do it. In time, all of that cable will sag down behind the insulation. For example, if you insulated this the way that was right there, you came back a year or so later, all of that, and you pulled that insulation off, all that cable would be bunched up sitting at the bottom of that application doing nothing. So that's improper attachment, also uneven disbursement of the cable, and not enough cable for this application, I can tell just by a quick look. So that would be a pretty bad installation there. And important as well, as I discussed, in that I like to have an understanding of all the way back from the transformer all the way to the end seal and everything, in that Low point conduit drains are extremely important because everything is ground fault protected. So you can see here, whenever a heat tracing system fails, or not even a heat tracing system failure, let's just say the heat tracing system is working fine, but there's a freeze up. I guess human nature that everyone sort of gravitates toward, it's the heating system, it's the heating cable, oh, it probably tripped, it's not working. When really it could, 9 times out of 10, heating, when there are freeze ups, and there's a heating, electrical heat tracing or self-regulating system on it, 9 times out of 10, it's an insulation issue or something in the conduit and wire. Not saying that we don't run into numerous problems with the heating cable itself, but just statistically, a lot of times if there is a freeze up, it is an insulation issue. The insulation is the most difficult system out of all of these components in a system to maintain. You can imagine you have thousands of feet of insulation. There's jacketing and there's elbows. They're driving screws into the jacketing. They're caulking things. That's going to wear out. People are going to walk on the insulation. So I always try to coerce people to think like, hey, if there's a freeze up, let's look at everything. Let's not just say, oh, it's the heating cable, it's bad, someone didn't size something properly, so on and so forth. The first thing I typically go out and look at is the insulation system as well. That's typically the culprit. And this is just showing you, looks like they're wrapping some cable around some supports there improperly. That's definitely not enough cable on there. And again, someone must have got a discount on duct tape because there seems to be a lot used in these applications, which is incorrect. And so we'll talk a little bit about insulation and the importance now, and we see this often as well, is that insulation is often an afterthought, and we like to get involved in these projects early to have influence on the selection and types of materials used for insulation. In this application, you see here, you have a hard urethane insulation, and it's preformed for the size of the pipe. So there's a couple issues here that I see, is that on the top right, or you'll see the arrow, what they did to, for some reason they're using an under the insulation component, and instead of oversizing the insulation in an area to accommodate for the component, they just cut the insulation out. So if you looked at that with a thermal camera, you would see a huge amount of heat pouring out of that area right there. Second thing they did was they didn't oversize the insulation ID to compensate for the heating cable. So for example, and it happens very often, if you have an application where you have a 2-inch diameter pipe, and then people say, oh, I need 2-inch thick insulation. So they'll call up and they'll get their insulation. They'll say, I have a 2-inch pipe, so I need a 2-inch ID preformed insulation that's 2 inches thick, which sounds great. However, when you have that heating cable on there, that's taking additional space. So what we recommend is that, for example, if you have a 2-inch diameter pipe, order 2.5-inch ID preformed insulation that's 2-inch thick. That way it gives that space in there, and you're not carving out rigid insulation so that it fits, or you're not just jamming and compressing the insulation and losing its K factor or R value to compensate for that heating cable. So you sort of have to oversize your insulation, for lack of a better term, when you're heat tracing a pipe. And then it compounds itself and gets even more important when you get into small diameter piping, because there's even less tighter constraints on the installation of that. So you can see right here, they're carving out insulation instead of oversizing it, which is always bad. Yeah, it'll look good. That's the material they had to work with. But now you have a heating cable that you're taking out 1 inch or a 1/2 inch of that insulation when that heating cable was sized for a certain thickness, and now it's not. You can see on the right there, they really butchered that up to accommodate for the extra cable on there, when really they should have oversized the ID of that insulation. So in the bottom left, actually both of these, you'll see what happens when you basically don't oversize it and it's just one run. You can't get the insulation to properly close around that pipe. It's designed to seal up real nice and neat and keep all that heat in. Right there, all on the entire length of the pipe, you're going to have heat, energy rushing right out of that. So that it may seem minimal, but that is a big heat loss. When you start getting into really low temperatures and higher maintained temperatures especially, you will have a tremendous amount of heat leaving out of that area, and simply because they didn't oversize the insulation by a 1/2 inch. And it's a shame, because a lot of times sometimes the cost is nothing or hardly anything for simply oversizing it. It's just really just choosing the right product for a much more robust system. And that's all I had. I'm sorry I went over. I think I was supposed to do a half an hour, but it looks like I did an hour. So if anyone has any questions, feel free to ask away. Of course, all my contact information is available. I'm sure Megan will be sending some information out following this, as well as a link. I'll send her to the installation video and the self-regulating technology video. So if there's anything you have now, ask away. If not, call me, shoot me an email, and we'll go from there. And back to you, Megan.
Thanks a lot, Ryan. If no one else has questions, we'll sign off for the day. But again, any questions, you can reach out to Eastern Controls or Ryan directly. Thanks, everyone, for your time.
Thanks, everyone. Take care.
Thanks, Ryan.